Okay, as Mr. Varney would say, of this packet, this is the beefy unit. We're now doing 6.2, which is the unit circle approach to trigonometric functions. Okay, it's going to be embedded on what we've already seen, hopefully, in a geometry class, the SOHCAHTOA definitions of trigonometry, where if you have a right angle and an acute angle, so you have a right triangle, with an acute angle, the angle that's opposite from the angle is called, given angle is opposite. The side that's next to it is called adjacent, and then of course the longest side of the right triangle is called the hypotenuse. From there, we could say that we define the sine to be the opposite over hypotenuse, that's the SO. We define cosine to be adjacent over hypotenuse, that's the A. And then we define the tangent to be the opposite over the adjacent, which is the OA. So we get the SO, sine, SO, cosine, ka, and then tangent, TOA. To some students, it's brand new here. These other trig functions, cosecant, secant, and cotangent, are the reciprocals of the sine, the cosine, and the tangent. So the cosecant, thus, is the hypotenuse over the opposite, because it's reciprocal of sine. Cosine goes to secant, which is a hypotenuse over an adjacent, and then the TOA, the tangent of opposite over adjacent, becomes a cotangent of adjacent over opposite. Okay, do not confuse these with inverses, right? These are not inverses, they're reciprocals. Notice there are some interesting relationships in here. Since tangent is opposite over adjacent, that's actually the same as opposite over hypotenuse and adjacent over hypotenuse, right? Because the h's would cancel out. So tangent is actually the same as sine over cosine. Cosecant is the reciprocal of sine, literally. Secant is the reciprocal of cosine. Cotangent's the reciprocal of tangent, and it's also a ratio of cosine to sine. And these all come from that basic SOHCAHTOA definition. Okay, now in past classes, you almost certainly saw 30, 60, 90 triangles. 30, 60, 90 triangles. So here we have a 30, 60, 90 triangle labeled with a hypotenuse of 1. Now, the 30, 60, 90, this was 2x. This side down here opposite the 30 was x, and this side was x rad 3. So what we're seeing here is that if c equals 1, then to get down to a, we would have to divide by 2, which means we get a 1/2 for a. And then we would have to divide, or take this side and multiply it by rad 3, which would mean the b would be a rad 3 over 2. So that's the b side and the a side. And with those numbers labeled, I'm now going to calculate the trig functions asked for below. So sine of 30 is from the 30-degree angle. We're going to go opposite 1/2 over hypotenuse. 1/2 over 1 is 1/2. Cosine of 30 is going to be rad 3 over 2 over 1. And the tangent of 30 is going to be the opposite over the adjacent. So it'll be 1/2 over rad 3 over 2. And so I typically write this as 1 over rad 3 because I'll cancel out those 2's. Nicely, the cosecant is just the reciprocal of the sine, so that one comes automatic. Secant is the reciprocal of cosine, and cotangent's the reciprocal of tangent, so those ones come along for free. Sine of 60 means now I'm looking at this angle as my beginning, so opposite over hypotenuse is now going to become a rad 3 over 2. The cosine is going to be a 1/2, and the tangent is going to be the rad 3. But then that just means that if I reciprocal, I'm going to get a 2 over radical 3, a 2, and a 1 over rad 3. So that's all 6 trig values on both 30 and 60-degree angles. Since similar triangles have proportional side length, changing the hypotenuse isn't actually going to change the values of the trig functions because, for example, the 1 over 2, if the 1 became a 2, the 2 would just simply become a 4, right? If the hypotenuse up here was a different number. So if this was a 2, this number would be a 1, and you'd get a ratio of a 1 over 2. The ratios don't change because the sides are proportional. Let's find the exact values of these now. So we have the 30, 60, 90 we just did above and filled in that chart. So what is the sine of pi over 3? The sine of pi over 3 is, well, remember that pi over 3 is 60 degrees, so it's actually just the sine of the 60 degrees, which is a rad 3 over 2. Cosine of pi over 3 cosine of pi over 3, that means the cosine of the 60-degree angle. Remember, that's a 60-degree angle. The cosine of the 60 is 1/2. The sine of the 60 is rad 3 over 2. And so as we square these, we get 1/4 plus 3/4, which gives me 1. Finally, the tangent of the pi over 3, so the tangent of the pi over 3 would be, let's see, the tangent was the radical 3, and the cotangent was the reciprocal of that, which is a 1 over rad 3. So you can leave it like this, or I guess we could combine denominators here if we wished and make it a, what would it be? It'd be a 3 plus, let's see, it'd be a rad 3 times rad 3 plus 1 over rad 3. Right, getting a common denominator, so it looks like we would end up getting 3 plus 1, which is 4 over rad 3. Okay. Besides the 30, 60, 90 triangle, another triangle we know and love is the 45, 45, 90. In this case, if the hypotenuse were 1, recall that this had ratios of x, x, x rad 2, and therefore if we wanted to get the x side, we would have to take the 1 and divide it by radical 2. Let's rationalize this one because it's a very important number that happens a lot. We'll call this side rad 2 over 2. And then since it's an isosceles triangle, that means this side over here will just also be rad 2 over 2. So, sine of 45 degrees, opposite over hypotenuse, rad 2 over 2. Cosine 45, also rad 2 over 2. Tangent 45 would be the sine over the cosine, or the opposite over the adjacent, and that's rad 2 over 2 over rad 2 over 2, but that of course is just 1. Next, let's do the reciprocals of these. I'll do this one first. The reciprocal of 1 is 1. The reciprocal of 1 over rad 2 is just rad 2. It turns out that's the same as 2 over rad 2 with rationalization. And then this is the same because it's the same, it's an isosceles triangle. Okay, again, changing the c is only going to change the way that the numbers work in here. So if we had changed the c, this side would be 2 now all of a sudden, and then these two sides would become rad 2s. And so you can just see the ratios in another way, rad 2 over 2, rad 2 over 2, and 1. But it doesn't change the value of the ratio. So let's calculate these now. The secant of 45 degrees, I actually can still see it there, is radical 2. And the tangent of 45 degrees is 1. So that's rad 2 plus 1. 2. Sine pi over 4. Pi over 4 is the 45 degree angle. So sine of pi over 4 is rad 2 over 2 plus radical 2 times the tangent of pi over 4, which is 1. So you can see here the 2's cancel. So we have a rad 2 plus a rad 2, which means we have 2 rad 2's. Sine of pi over 4, remember pi over 4 is still 45 degrees, so this is rad 2 over 2. And cosine of pi over 3 was on the other page. The cosine of pi over 3 was 1/2, because pi over 3 is the 60 degree angle. So this, of course, becomes rad 2 plus 1 over 2. Circle definition, not yet unit circle, but just circle. So if you look at what's going on in here, here's a circle that has a radius of r. The coordinates x, y can be thought of as the horizontal distance of the point and the vertical for the y. If you notice, from this angle now, sine of theta would be opposite over hypotenuse, which is y over r. Cosine is adjacent over hypotenuse, which would be x over r. And the tangent is the opposite over the adjacent, which is y over x. Furthermore, cosecant is the reciprocal of sine, secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. These other pieces here are necessary because the radius will never be 0 in a circle, but lengths can be 0. For example, if we were at any of the quadrantal angles, the ones located at the 90 degrees or the pi over 2, at this point you would have a, sorry I got that backwards, it would be an x-coordinate of 0 and a y-coordinate of 1. So it's potential that you get x's and y's that are zeros, and that causes domain issues. So with that in mind, let's state the domains of each trig function. So remember, the sine of theta was over r. R is never 0. So this is going to have a domain, sine of theta is going to have a domain of all real numbers. This is also true about the cosine. You can stick in any real number, any angle works. Tangent, you cannot have x equal to 0. Remember, x is the horizontal distance. So that means you won't be able to do pi over 2, 3 pi over 2, or multiples of those that are coterminal, moving around the circle. Turns out those are 1 pi over 2, 3 pi over 2, dot, 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 dot. These are the odd multiples of pi over 2. You cannot have the x to be 0. Also, you can't let the x be 0 for the secant. So that gives us the secant for free. So the secant, the domain is, I shouldn't say odd multiples, I should say not odd, because those are the ones that are not allowed. Same here. Not odd multiples of pi over 2. These are the ones that are not allowed because they cause the x to be 0. How about for the y's? So here we need to make sure that y is not 0 for the cotangent and the cosecant. Those are going to occur here at 0 and over here at pi. These are the places where you get y coordinates that are 0. And of course anything that would be coterminal with these, so not just pi, but also 3 pi, 5 pi. And over here it wouldn't just be 0, it would also be 2 pi, 4 pi, and etc. So of course, if those are the illegal spots, that means that the answer down here is you're going to have to make sure that you are not multiples of pi. You can't be 1 pi, 2 pi, 3 pi, 4 pi. That's also true for the cotangent. Not multiples of pi. Okay, extending this idea a little bit, let's try to do a problem with it now. The terminal side of an angle in standard position intersects the point 1 comma radical 3. 1 comma radical 3. 1 comma radical 3. Which lies on a circle of radius 2. This is not a great drawing of a circle of radius 2. But close-ish. Okay. Find the exact value of the 6 trig values. So the terminal side of an angle. So the angle is going through here. Okay, it goes through this point at 1 comma rad 3, but unfortunately this is on a circle that has a radius of 2. So that means that this side down here is 1, this side is rad 3, and this is a 2. Looks a whole lot like our 30, 60, 90 triangle, doesn't it? Notice that the sine of 30 is the opposite over hypotenuse, the cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. To get the cosecant, this is a reciprocal. Reciprocal of cosine gives you secant, and the reciprocal of tangent gives you the cotangent. Here's another example. This time we're going through the point 3 comma negative 5. So 1, 2, 3. 1, 2, 3, 4, 5 puts me down here. So this side is 3. This side is negative 5. And our angle is now right here. Right? Technically, if we think of it counterclockwise, it's actually this guy. But both of these are coterminal. It's not going to change the sides. Notice that we can figure out the third side of this triangle by the Pythagorean theorem. 3 squared plus negative 5 squared equals 34. So this must be radical 34. And therefore, the sine of this angle is opposite over hypotenuse. The cosine is the adjacent over the hypotenuse. And the tangent is the opposite over the adjacent. To get these other angles, we just reciprocal. Rad 34 over 5, that one's negative. Rad 34 over 3, and then negative 3/5. Okay, now the denouement, the unit circle. The unit circle is a more general definition where instead of allowing, I guess it's less general actually technically, because instead of allowing any radius, we just make the radius of the circle be 1. Remember before, the definition of sine theta was y over r. So if we just let r equal 1, that means that your sine of theta is simply going to be the y-coordinate of that point on the circle. Similarly, cosine was x over r, but now it just becomes x because the radius is 1. And that means if you can figure out the coordinates of points on the unit circle, you're actually being provided the cosine and the sine. As before, cosecant is reciprocal of sine, secant is reciprocal of cosine, and tangent's the ratio of the sine and the cosine. Cotangent reciprocal of tangent. So this is the stuff that dreams are made out of now. This makes things so easy if you know coordinates on the unit circle. So for sine of 90 degrees, let's do these quadrantal angles now specifically or carefully. So go to a 90-degree angle, which is located at the top of the circle. Its coordinates are 0, 1. As we discussed above, sine is the y-coordinate. So the y-coordinate is 1. That gives us the answer to this problem. 3 pi over 2, right, so 90 degrees is at top. 3 pi over 2 was the measurement down here at the 270 degree marker. So down here your coordinates are 0, 1, which means the cosine is simply going to be 0. 0 degrees, located over here at the right, that's 1, 0. And tangent was sine over cosine, was y over x. So y over x would be 0 over 1, which is 0. 180 degrees is over at the far left, and that had coordinates of -1, 0. So in this case, the sine would be the y-coordinate, which is the 0. 0 radians, that happens to be the same place as 0 degrees, of course, but now it's asking for the secant. So remember that secant is 1 over cosine of 0. It's 1 over the x-coordinate. So go to the 0, there's a 1. X-coordinate is 1, so it's 1 over 1, and that's 1. And finally, the cosecant of -270, the cosecant is 1 over the sine, -270. -270 means we're moving in a clockwise direction, so -270 is actually the angle up here at the top. Its sine value is +1, so this becomes 1 over 1, also known as 1. So the quadrantal angles are either zeros or ones most of the time. Okay, in order to find angles that are not quadrantal and not in the first quadrant, it's often useful to think about their inclination from the x-axis. We refer to these as reference angles. When I draw my unit circle, these are the ones I'm boxing together. This is a table that gives you some formulae that you can work with that would allow you to be able to find the reference angles. So as an example, let's go down and find some reference angles. So 135 degrees. I'm going to do this geometrically because it's how I think instead of doing it with the actual calculations, but you have these formulas up here that you could use. So I know a 135 degree angle looks like this. I like to, and the way I calculate my reference angles is I think how far is it from here to the closest x-axis? 180 minus the 135 means my reference angle is going to be 45 degrees. -310. -310 means that I'm moving in a clockwise direction. So I have to go all 270 and then 40 more. So that's 310 degrees negative. And so, of course, since a full circle is 360, that means I'm missing 50 degrees more. So that's my reference angle here. The reference is a 50-degree angle. -2 pi over 3. -2 pi over 3 would be located right here. Of course, this is pi radians, so -2 pi over 3. Sorry, -2 pi over 3 is actually located over here. -2 pi over 3. How far am I from the pi measurement that would locate right here? So 2 pi over 3 is, of course, 1 pi over 3 away from pi. So this reference angle is going to be pi over 3. 11 pi over 6 is the angle down here, which is only pi over 6 away from the x-axis. 510 is big, right? So that's going to be 360 degrees plus an extra 150 degrees. And so it's coterminal with 150 degrees. And of course, how far is that away from the 180 marker? That's going to be only 30 degrees away. And then negative 7 pi over 6 is the one that's located in the negative direction, a little bit more than half a circle, so it's going to be right here. Right, that's the negative 7 pi over 6. Negative 7 pi over 6. But of course, again, how far away are we from the x-axis? We've only gone 1 pi over 6 beyond it, so its reference angle is a pi over 6. Okay, so now special angles. 150 degree angle is the blue angle, right? It's located over here in quadrant 2. Its reference angle is 30 degrees because that's how much further you had to go to get to the x-axis. Its reference angle, since the 30 degree marker, it's going to be the same angle or parts as the 30 degree marker. The 30 degree angle had 1 there, 1/2 here, and rad 3 over 2 on this side. And again, I'm a unit circle person, so I could totally understand some people just labeling it like this and then doing your SIGN signs later. But I'm a unit circle person, so I'm actually thinking of the coordinates right here as 1/2 comma negative rad 3 over 2. So when I do these in class, I'll usually label this side as a negative, even though I know lengths aren't technically negative. But now notice the joy of this, right? The sign of 150 is just simply, whoops, I put these backwards. That's a plus. That's a minus. No. Oh, no, I reversed the coordinate sign, sorry. The x is negative rad 3 over 2. The y is 1/2. My apologies there. Okay, 1/2 is the y, negative rad 3 over 2 is the x. So when I now ask for the sine of 150, sine of 150 is the y coordinate. Cosine of 150 is the x coordinate. Tangent is the ratio of these two, which would be a 1 over a rad 3 negative. And then over here, these are all reciprocals of the originals. So that's 2. This is negative 2 over rad 3. And this one is negative rad 3. How about a 4 pi over 3? So now they want us to draw a 4 pi over 3, so I'll do this my way. 4 pi over 3 is the one that comes down here. Since I know my unit circle, which is what I'm going to encourage you all to do too, I can see that I have a little x coordinate that's negative, and I have a big y coordinate that's negative. And so knowing the coordinates of the point on the unit circle located at 4 pi over 3 allows me to come straight over here and just say, well, the sine is negative rad 3 over 2. The cosine is negative 1/2. Take the ratio. Reciprocal, reciprocal, and reciprocal. And that completes those 6 values of that special angle. Let's find the exact value of these expressions then. So using my unit circle, thinking of my unit circle in the background, pi over 3 is located right here. And so its tangent is the ratio of the sine over the cosine. So it's big over small. That's radical 3. 7 pi over 6 is located over here. So the tangent of that one is going to also be a positive because it's negative over negative, but it's big over or small over big. So that's going to be 1 over rad 3. Pi over 6 is the one located down here. Pi over 6, little y value, that's the sine, so that's 1/2. Cosine of 5 pi over 4, 5 pi over 4 spits me over here, which was the negative rad 2 over 2, negative rad 2 over 2. So we have subtracting a negative rad 2 over 2. Maybe I'll do a little simplification there since they have the common denominator already. How about these two? Cosine of 135. 135 is located right here. It has coordinates of negative rad 2 over 2, rad 2 over 2. So I have 5 times the cosine, negative rad 2 over 2, minus 8 times the sine of 270. 270 is down here at the bottom of the circle, which is 0, negative 1. So its sine is negative 1. So it looks like we're getting a negative 5 rad 2 over 2 plus 8. And then finally, 3 pi is a whole circle plus another pi, negative 1 comma 0. Secant is the reciprocal of the cosine, so the reciprocal of negative 1, which is also negative 1. 4 pi over 3 is located down here. That's at negative 1/2 negative rad 3 over 2. And so its sine value is negative rad 3 over 2, and thus its cosecant value is 2 over rad 3. So the final answer I'm getting here is negative 1 plus 2 over rad 3, barring any simplification you wish to do. Okay, last cool problem for this doozy of a lesson here. Sine of 20, okay, let's draw a picture here. Sine of 20 is some y value. Let's call this a 20-degree angle. It's some y value. It's not unit circle. I don't know where these things are, but I'm drawing a little circle here. Sine of 20 has some kind of y value. 160 is over here. Notice it has the same y coordinate. That's the use of the reference angles. Turns out the reference angle is 20, so we know that the y coordinates and x coordinates are the same up to the sine. But since it's above the axis, that's a y. 200 degrees is 20 degrees below the axis. So that just simply means that that's going to be a negative y. And then 340 is also the same reference angle. It's going to be an x comma negative y. There's our negative y. And so the end result of adding up these 4 angles, that I don't have any idea what the values are, but I know that their sum is going to be 0. Since I can't project my calculator here, I'm not going to do this one, but ask me in class if you need to learn how to switch your calculator into degree versus radian mode.